Swayam Prabha. Digital India. Educated India.
Okay, so we will continue with more approximation algorithms. So last time we saw approximation algorithms for vertex cover and TSP, and we saw two approximation for vertex cover. For TSP we saw 2 and 1.5 for the metric version of TSP. For general TSP we argued that no polynomial factor approximation is possible. Okay. So, today we will look at 2-3 more problems. So, the first problem I want to look at is a scheduling problem. There are lots of versions of scheduling problem. So, we will look at a very simple version and look at some simple approximation algorithms. Okay. So, the input has n jobs and some m machines, and each job has a time it takes on any of the machines. Okay. And our job is to schedule these jobs in the m machines, so that no particular machine is overloaded. Okay. So, what does that mean? What is the quantity we are trying to minimize? The total time some machine takes, right. So, you are going to assign these n tasks to the m machines and look at any of the machine and look at the overall time it is spending, that maximum time which we want to minimize. Okay. So, what does this mean? Minimize the term, what is the term is called make span, and what is this? This is over all the machines. If you look at this is the AI, suppose is the jobs assigned to machine I. Right, we want to minimize the maximum load on any machine. Okay, so, it is an optimization problem. You have this, and so there are lots of variations of this. For example, we assume that you take this job and assign it to any of the machine, it is going to take the same time T I, but this may not be true, right. Some job on some machine may take more time, some machine may take less time. So, you can have that variation, and sometimes you after you assign, part of the work is done, can you preempt it? Sometimes that is allowed. So, these are more general complicated problems, and all of them are hard, and approximation algorithms for all of these are interesting current topic actually. Okay. There are a lot of research currently that goes on in various versions of this scheduling problem. Okay. So, let us look at an example. Let us say we have 3 machines, 6 jobs with the time it takes is this. Okay. So, let us call this 1, 2, 3, 4, 5, 6, and I want to assign these 6 jobs to 3 machines. So, let us think of some assignment. This is machine 1, machine 2 and machine 3. I may assign jobs 1 and 4 here, maybe 2 and 3 here, and maybe 5 and 6 here. Okay. And what is the make span here? What is the make span here? What is the maximum time spent by any machine? That is what is called 8. Where is it? M1, because I am assigning 1 and 4. So, that is 2 plus 6. So, that make span is 8. Right. Suppose I do the following assignment. So, maybe just job 4 alone here, 2 and 3 here, and 1, 5, 6 here. What is the make span? 7, right. So, so you understand the goal now, right. You have these 6 machines, 6 jobs, 3 machines, you want to assign them such that no machine is heavily loaded, and you want to minimize the make span. So, there are if you want to think of a brute force algorithm, there are lots of possible assignments, and how many assignments, because each of the n jobs can go to any of the m machines. So, that is like an m power n kind of an assignment, and so it is exponential algorithm, and the decision version of the question would be, is there an assignment with the make span at most certain quantity? It is an NP, because you can just give an assignment, you can prove it NP hard. Okay. This is sort of like a subset sum kind of a problem. Okay. So, we are not going to do NP hardness, we can prove that it is NP hard, but what I am going to do is to look at a simple greedy algorithm and analyze, and not analyze the running time. We will do that, but that will be the easy job, but analyze the quality of the solution, how bad the solution I produce compared to the optimum. Okay. So, what would be a simple greedy algorithm? So, so there are n jobs, right. I am going to look at these jobs in some arbitrary order, they are given in some arbitrary order, and what is my task? I have to assign job number I to one of the machines. What is the natural machine to assign? So far, whatever job has taken less time totally, just assign it to that, whatever has the less load so far. So, assign job I to the machine that has the least load so far. Right. This English term can be mathematically made precise, right. So, you have T1, T2, T I minus 1 jobs 1 to I minus 1 assigned. Out of them, look at each of the machines, pick the max of the summation T i's assigned to each of them, and whichever is the lowest, right, not the max, min of them, and whichever is the lowest, just go and assign your job to that. Okay. So, for example, if first of all, this is you can easily implement this in some n square time, right. Every time you have to find some min computation. So, it is a polynomial time computation. We are not so worried about can we improve it. Yes, that will be one important point, but that is not the focus of this set of lectures. Okay. So, if I do this greedy algorithm on this sequence, then what would I do? On M1 I am going to give 2, M2 will take 3, M3 will take 4, and then 6 comes, I am going to assign 6 here, and then 2 comes, I will assign it here and then the next 2 will be assigned here. Why did I assign 6 here? Because this machine had the least load at that point among the 2, 3, 4. So, I went and kept 6 here. The next job was 2, and among all these 3 machines, this had load of 3, this had load of 4, and this had a load of 8. So, I picked the one which is the least load and I assigned it here, and the last machine by the same token gets assigned here with a make span of 8. So, clearly this is an ordering where the make span is not optimal, because there is at least a better assignment possible. Okay. Even better may be possible, I have not checked, but okay. So, it is a simple greedy algorithm, and as I said, for many of these problems it is not that hard to come up with some heuristic, but the challenge is to see the solution produced, how bad it is to the optimum. Okay. The claim I want to do, if T is the make span for this algorithm, T is at most 2 times opt. Okay, so, it is a ratio 2 approximation algorithm. Again, the challenge is that I do not know opt, I do not know a way of even computing it, but we will use some lower bounds for opt to do this comparison. All right. So, let us understand what are some lower bounds for the opt. Okay. So, some sub claims, right. I want to say that optimum must be at least summation T I by m. Agreed? Because total amount of time required for assigning all the jobs is summation T I. So, at least one machine must take at least this much time, whatever the assignment is, right. So, the optimum must be at least this. So, this is one good lower bound we will start with, right. Let us try and think of a better lower bound. Can you think of a better lower bound? So, the problem, suppose the problem with this lower bound is, suppose you have one job which takes a huge amount of time and everybody else takes some tiny amount of time, and the average will be small. Okay. So, what would be a lower bound to capture this scenario? Max, sorry, what did you say? Yeah, so max, exactly, that is what he also said. So, another lower bound which we will use is T star is at least max of the time required. Look at the n jobs and pick the maximum. Any machine must take at least that much time, because this job has to be assigned somewhere. So, these are the 2 lower bounds. So, this what is the lower bound we used for minimum vertex cover? Matching. Any matching is a lower bound, right. What is the lower bound we used for the traveling salesman problem cost? Minimum spanning tree cost, right. So, first if you want to do your comparison of your solution with the optimum, you need some lower bound. For in the minimization case, you need lower bound. For maximization case, you need upper bound. Okay. We have not done maximization problems, I will do sometime. Okay, good. So, now let us come back to the proof of this claim. Right. These 2 claims are pretty easy to see. Yeah. So, let K be the machine that achieves the load of T, right. So, I assume that my algorithm after this assignment, this greedy algorithm, has a make span of T. So, now I go and say which machine has that load K, right. So, I have made my assignment to these m machines, and here is the machine K, which overall takes a load of T. So, look at the last job assigned to this machine. Okay. So, let j be the last job assigned to the machine M. Now, so this is think of this as horizontal line as the assignment, the time, right. Now, at this point, what can you say about the load of these machines? Greater than or equal to whatever the load at this point of the machine k is. Why? Because the greedy algorithm chose this machine to assign the job j, right. So, that means this was the least load machine at that time. So, everybody else had a load of at least that much, maybe equal to. Okay. So, but this is the sum of the time for all the machines except the jth machine, right. So, let me just write what I say, that load of machine k at that time, before, what do I mean by at that time, before assigning j, is at most summation T I equal to 1 to n, I not equal to j divided by m. Agreed? Because this sum, if you sum all the load of all the machines up to this point, they I mean not up to this point, because some of them may actually be going up, just before assigning this last job, some of them may go up to this point. Okay. Except this, so their total time summation T I minus the jth job divided by m, because this guy is the least load at that time. So, this load is at most this, right. Okay. But summation T I by m, we argued, is strictly less than or equal to the optimum, right. So, this quantity is strictly less than T star, because it is even missing the job j. Okay. Also, what do we know? T j is less than or equal to T star. The time for this machine is less than or equal to T star, because of our second lower bound. T star is at least the max of the T i's. So, in particular it is at least this particular T j. Okay. But what is the load of k? What is T? T now is this plus this, right. But this alone we already argued is at most T star, and this is at most T star. So, T is strictly actually less than 2 T star. Agreed? That is what we wanted to show, that the make span of the job, the machine. Questions? Not clear? I will go over it again.
Why you think summation over all time? Because at that time when job j must have been assigned to machine.
But I divided by m. So, this, if you look at, I want to get an upper bound for this time, that is all. Okay. But what do I know? That this was the least load. So, everybody else had at least this much. Okay. So, maybe, right. So, let us okay, let me get this slightly differently. Okay. The sum of the loads of all machines before the j was assigned, this is greater than or equal to whatever this load times m, right, load of k times m, because this is the least. Okay. But what is the sum of the loads of all machines? This is exactly equal to sum of the time, all the times except T j. So, this is equal to summation T I not equal to j, the sum. So, from here I get the load of k at that time is strictly less than or equal to summation T I this quantity whatever. Okay. So, now let us think about, I want to improve the approximation ratio, and okay, first of all, here is an example which will actually achieve an approximation ratio of 2. Okay. It's useful to have such example. Let us say n, the number of machines is m into m minus 1 plus 1. So, number of jobs, m is the number of machines. Okay. Each of these jobs have time 1, and this job has t equal to m. Okay. So, there are roughly about m square many jobs coming in, and we have to assign it to these m machines. All of these machines have time, they will take 1 unit of time, and this one alone takes m unit of time. Let us see what the greedy algorithm will do. What will the greedy algorithm do? It will m into m minus 1 machines, it will it will assign some m minus 1 machines here, m minus 1 machines here, and m minus 1 jobs here, m minus 1 jobs here. Right? The first job will go here, second job, third job, mth job, because they all have the same load. So, arbitrarily it will pick some machine, and it will pick the next job and so on. So, all the m minus 1 jobs, m minus 1 into m, all of them taking 1 unit will go here, and then there is this last job which takes m unit will come, and it gets arbitrarily assigned to somewhere because there is a tie. So, the m will come here. So, the total make span would be 2 m minus 1. Okay. But what would be an optimal way to do? Get the bigger job first, right. So, let us say I do the following. I take the job which takes the most time, which takes m unit of time, I am going to put it here. Okay. This is not greedy, because greedy will not do it, but this is what I am going to do. And after that, the remaining guys get assigned here. Right. So, there are, each of them will get m jobs, because m into m minus 1. What is the make span here? M, whereas here it is 2 m. So, the ratio is 2. Okay. So, greedy can be as bad as greedy's approximation ratio can be as bad as twice the optimum. We are just going to do that. Good. So, we are going to do that now. So, now the next algorithm, sort jobs in non increasing order of the times, then do the greedy. Okay, this is an extra overhead of about n log n on the running time, but let us see whether it improves, what happens to the approximation ratio. Okay, so, let us call this improved greedy. First of all, let us make some observation, right. If there are only m jobs, what can you say? Max of the jobs is the make span, and how would you assign it? Arbitrarily, just pick one job to first machine, second job second machine, and so on, and that is the optimal assignment, and the make span is the max of that, and that is also the optimum. We already argued optimum must be at least that, right. So, the any assignment, I mean not any assignment, you won't stupidly assign 2 jobs to one machine, because when somebody is free, any assignment that assigns each machine one job is optimum, right. So, the problem, the approximation, all that comes in only if there are strictly more than m jobs. Yeah. So, now here is the claim 1. Okay. So, let's say our jobs are, we have arranged it in decreasing order or non increasing order of their running times, right. Now, I want to say that, so now let us assume there are more than n jobs, then I claim that T star is greater than or equal to 2 T m plus 1. Do you see this? Yes? Why?
Because after assignment of first n jobs, so T1 will be the make span or the value that is maximum of overall
Yep.
machines. And when I add this to the first machine, I think
I may not add to the first machine, I don't know where.
any machine, so that will have the maximum now. Worst case, that will have the maximum now.
Yeah.
In the worst case,
So you are talking about the optimum. So, let us look at the optimum assignment. Okay. So, let us even ignore jobs after m plus 1. Let us even look at the first m plus 1 jobs and let us look at an optimum assignment. Clearly, one machine will have at least 2 jobs, because there are m plus 1 jobs, pigeonhole principle. One machine will have at least 2 jobs, and what would be the mix span there? At least 2 times T m plus 1, because T m plus 1 is the least among them. We have arranged this. So, that, right. So, the proof is, if you look at only the first m plus 1 jobs, at least one machine will have two jobs with a make span of this is in any assignment, okay, because we are not talking about one particular greedy or anything. Any assignment, any optimum assignment, at least one machine will have 2 jobs, and if you add the costs, because T m plus 1 is the least, their cost would be at least 2 times T m plus 1. Now, this is all I need to now more or less the proof is. Let us just come back to this argument, right. Now, look at this improved greedy, where we have organized first of all the times in non increasing order of the jobs, and then I am doing this greedy. Let us look at the job machine that has the maximum load, and let k be that machine, and let j be the last machine, that is job that is assigned to that. By our earlier argument, we know that the load here is at least T star, right. That is what we saw. Sorry, at most T star. This is it, right. The load of the machine before assigning j is at most T star was true even now, because the same argument, this averaging argument, and this machine's load is at most T m plus 1. Why? Because we have arranged all the jobs in decreasing order. What will the job assignment do for the first m machines? It will assign them all separately in each of the machines, because they are all, one machine has least load, 0 load. So, it will go and assign it there. So, only the m plus 1 or later machines get attached later. So, this job has cost at most T m plus 1, because job timings are decreasing. So, this has at most T m plus 1. So what? The T, the make span of the improved algorithm, at most T star plus T m plus 1. Right, I look at that job and remove the last machine. We argued that the load up to that point is at most T star. Now, the last machine, the last job number is at least m plus 1 and the timings are all decreasing. So, this guy's job time is at most T m plus 1, but we already argued T m plus 1 is at most T star by 2. Here it is, right. So, what? So, what have we done? We have improved the approximation ratio from 2 to 1.5. Is this clear? You don't seem convinced.
I have an example. Assume that m machines.
No, where is the problem in the argument?
There's no problem.
Okay.
I have an example.
Okay.
Let us consider m machines.
Okay.
With the jobs be m plus 1. Consider the job as unique value.
Unique
same
time.
value.
All of them are the same value. Okay. So, there are m plus 1 jobs, m plus 1 jobs,
m plus 1.
m plus 1 jobs, all of them have the same time. Okay. So, here it is, right. So, we had a very simple scheduling, greedy scheduling. I mean, again I want to emphasize, coming up with some greedy algorithms is not that hard. It's something very natural. Next step is actually implementing and doing a running time. Maybe a little more involved, not that hard. But the challenge is that whatever the solution I produce, to relate that to the optimum is the hardest thing in this area. Okay. So, we saw that the very simple greedy algorithm gives you 2 approximation, and with this little idea, why don't we order the jobs in decreasing order and then do this, it gives you 1.5 approximation. And it turns out that actually even there are better algorithms known, you can get to any epsilon. We won't talk about them now here, but these are called polynomial time approximation scheme, that you can get arbitrarily close to 1, the approximation ratio. Okay. Then you should ask, why don't I put epsilon equal to 0, right? What happens? Do I get optimum? So, there is somewhere I should pay. Where do you think I should pay cost? Running time will increase. So, the running time will be something like n power 1 by epsilon. So, as you want closer and closer to the optimum, the running time will increase. Okay. It could be even some function of 1 over epsilon, it could be 1 over epsilon cubed or something like that. But I mean, these algorithms are not that hard, some rounding you need to do. In fact, it is a 1-page algorithm, but it requires some careful analysis. But this term is useful, it is polynomial time approximation scheme.